We're going to talk about hyperbolic functions in this video, but in order to do that, we're going to motivate it by talking about trigonometric functions and see how they're related. So we already know all of this about trigonometric functions. We know that sine of theta is y over r if we're looking at a unit circle and so on with all of these other things. We also know that cosecant, secant, and cotangent are the reciprocal functions, and we know that tangent we can write as sine over cosine, and cotangent we can write as cosine over sine. These are all things that we already know. We also know that trigonometric functions have certain derivatives that we have learned over the course of the school year, and we've put them in this little diagram. And we know that for sine and cosine, at least, if I take the derivative of sine, I get cosine. And then if I take the derivative of cosine, I get negative sine. And then if I continue the pattern within 4 iterations of the pattern, I get back where I started. So these are all things that we already know. So notice that I'm now back where I started, basically. Um, One of the special properties of trig functions that we have talked about, but I don't know if we've really kind of focused on it too much, is that if I have a parameterization cosine comma sine, and t goes from 0 to 2 pi, I start here, and then that takes me and traces the entire circle. So that actually traces the unit circle x squared plus y squared equals 1. So that is centered at the origin. This is something that we have talked about in the past. And this also kind of makes some sense of that Pythagorean identity that we learn in Algebra 2 and pre-calculus that we use a lot, where cosine squared plus sine squared equals 1, or sine squared plus cosine squared equals 1. This makes some sense of that because if I take cosine and sine and I sub them in, I end up getting 1. So it ends up making some sense, in addition to the sense that it made when we did this kind of substitution over here, where sine squared plus cosine squared can be replaced by y over r squared and x over r squared. So if I know that equals 1, and then I multiply the r squared over, I get x squared plus y squared equals r squared, which I know is the equation of a circle. So these are all things that have kind of made sense in the past. Now, we've also used trig functions numerous times to make circles and ellipses, and you can also use them to make hyperbolas and tons of other things when you parameterize things. So if I use the parameterization t from 0 to 2 pi, I have a variety of different things. I can do a circle where, notice that I flipped where the sine and cosine was. That basically just means I trace the unit circle in a different way. And you'll be seeing these things on the screen from Desmos as I'm talking about it. This one is going to be tracing a circle of radius 2 instead of a circle of radius 1, and it traces it in the same direction as the original parameterization with cosine and sine. Negative cosine and sine is going to trace a unit circle again. It's just going to trace it starting over here. And then I can also do horizontal and vertical shifts. And then I have a radius of 2. So as you'll see, this is centered at 3, 7, and I have a radius of 2 on that. I can also do ellipses. So this is an ellipse with x radius 3, y radius 5, and it's going to start over here and kind of be drawn like this. This one is going to have a center at negative 4 comma 7, and it's going to have an x radius of 3, a y radius of 2, and it's going to be traced in the same direction as we just did over here. Then we can also do hyperbolas with secant tangent. So if I have secant and then tangent, that traces a hyperbola kind of like this. and then it finishes off this way. Tangent secant is going to be a hyperbola in the y direction, so it will look something like this. Then I can have a hyperbola where I do some horizontal vertical shifts, and then this kind of alters the length of the hyperbola, so like where the asymptotes are. So for example, this hyperbola would have asymptotes with slope plus or minus 7/3, and it essentially changes the way that the box that you conduct the hyperbola is formed. And I graph my hyperbola looking something like that, which you would see on the screen. Okay, now all of that is just a preface for defining hyperbolic functions. So hyperbolic functions are something that a lot of your classes are going to require you to understand in college, but it's not part of the AP curriculum, so that's why I wanted to make a video on it. Let's say we have cosh and sinh. That's typically how they would say it, cosh and sinh. So that's the hyperbolic cosine and hyperbolic sine functions. So essentially, instead of parametrizing a unit circle, this is going to parametrize a unit hyperbola. It's going to parametrize a unit hyperbola. So it's going to be centered at 1, 0, but it only does the right side of the hyperbola, even if I'm going from negative infinity to infinity. So this is kind of what's happening. Um, if I flip where the parameterizations are, things can change in terms of whether I'm doing the right side or the left side, or if I flip sine, hyperbolic sine and hyperbolic cosine, then maybe I could do an up and down hyperbola instead. But notice that I'm having a hyperbola here, and then the Pythagorean identity for hyperbolic trig functions that you will use is actually looking like a hyperbola instead of looking like the Pythagorean theorem or looking like the equation of a circle. It kind of looks like the equation of a hyperbola instead. So this is what a hyperbolic function is. Now, you can do similar things to get more parameterizations, and I'll show these on the screen as I'm talking about them. But square hyperbolas, so a square hyperbola just means that the box that makes these things is a square. So notice that um, the 1 and 2 are kind of the same. So that means that my function is going to have a slope plus or minus 1 for um, the asymptotes. But as you can see, I'm putting all of these on the side of the screen. So the hyperbolic sine and cosine being switched from the original. So the original was up here. Switching them, basically all that does is it means that I get the top part of a hyperbola. This is going to be the bottom part of a hyperbola, except it's going to be centered, or the vertex is going to be at 2, 0, and I still only get the right side. Now, when I do this one, what I'm going to notice is that I get the left side of a hyperbola. So my x values are all going to be negatives. Um, and then when I look at this one, I have a shift that's going on, but I still get just the right side. Other hyperbolas, what I mean by that is that the slopes are not plus or minus 1 of the asymptotes. So I have this one, I only get the right side, and this one, I also only get the right side. All these have parameters negative infinity to infinity, what I'm showing you on the screen. And also notice you only get one side of the hyperbola in these parameterizations, which is a little strange. Because when we were using the trig functions, we were getting the full hyperbola and stuff like that. But one of the reasons why we may want to use and learn these functions is that they have real practical applications. So for example, um, if I have y equals uh, a times the hyperbolic cosine of x over a, This actually models a cable or a wire that is being held up by um, two fixed poles. And so that kind of models the path that that cable takes. You'll see it a lot in electrical wires, and if chains are being held up on a fence, this function models that. And so this hyperbolic sine and cosine stuff actually has a lot of applications for people in certain mathematically based fields like engineering and things like that. But also notice that you can model circles and ellipses here. So hyperbolic secant and hyperbolic tangent. Uh, we what we'll see is we'll end up modeling half of a circle. This one models half of an ellipse, and um, this one models half of an ellipse as well, just with a shift. Amazingly, there are actually nice functions for this. So hyperbolic sine and hyperbolic cosine are actually these functions that can be defined with exponential functions, e to the x and e to the negative x. So the hyperbolic cosine is actually the average of e to the x and e to the negative x. And then the hyperbolic sine is actually, if we were thinking about it in terms of like these two things being their own separate y values, it would be half the distance between those two y values. So it is half the distance between y equals e to the x and y equals e to the negative x. So there are amazingly some nice functions for this. And then some other things that are really neat are that the properties are actually similar to trig properties. That begs the question, what is hyperbolic tangent? Well, I'm kind of aware that sine over cosine is tangent. So I wonder if um, the hyperbolic sine over the hyperbolic cosine is hyperbolic tangent. And so it actually is. So if I just take these two things and divide them, I get e to the x minus e to the negative x over e to the x plus e to the negative x. That gets me hyperbolic tangent. Uh, and then all of these things are just the reciprocal functions. So I have 2 over e to the x minus e to the negative x for hyperbolic cosecant, 2 over e to the x plus e to the negative x for hyperbolic secant, and I have e to the x plus e to the negative x over e to the x minus e to the negative x for hyperbolic cotangent. So those are kind of interesting things. And then we also have some derivatives of hyperbolic functions. There are two slight differences. Notice that the derivative of cosine, the hyperbolic cosine, is not negative hyperbolic sine. Notice that it stays positive. So these actually cycle back and forth after only 2 derivatives instead of 4. And then there's one other slight difference, that the derivative of the hyperbolic secant is actually now negative, whereas before that was positive. So these are the derivatives of hyperbolic functions. You can also find some other things that are true about hyperbolic functions that mimic what happens with trig functions, but aren't exactly the same. So, for example, we know that cosine of x plus or minus y is cosine x, cosine y, and then we switch the sign. So that's something that's true about cosine. When I teach that in Algebra 2, I say the cosine coalition changes the sign. But if I'm dealing with hyperbolic cosine, it actually does something very similar. So I have cosine, hyperbolic cosine. X, hyperbolic cosine y. I keep the sign the same. Hyperbolic sine of x, hyperbolic sine of y. And so there are other things that are very similar in relationship. Um, but something that you have to kind of keep in mind when we're doing this is that a lot of like these hyperbolic functions are actually defined in terms of exponential values. And so that actually makes them relatively simple to be manipulating. One more thing that I kind of want to talk about is let's talk about the Taylor series. Now, what happens if I take a look at the hyperbolic sine? So hyperbolic sine I know is e to the x minus e to the negative x over 2. Um, and well, if I take a look at the Taylor series for this, if I sub in 0, I get e minus e, which is 0. Now, when I take the derivative of this, I know that the derivative is cosine or hyperbolic cosine. And you can actually prove that. So this is like the 0th derivative. This is the first derivative. If I sub in, I'm finding all of these values at x equals 0. So if I sub in 0, I get 1 plus 1, which is 2, and 2 divided by 2 is 1. Now, remember, the derivative of hyperbolic cosine is right back to hyperbolic sine. So this is the second derivative. Then this one's the third derivative. Then this one's the fourth derivative, fifth derivative, sixth derivative, seventh derivative, and so on. So basically, it alternates between 0 and 1 for my derivatives all the time. So if I look at the Taylor series for hyperbolic sine, I have 0 plus 1 x over 1 factorial, because this is a Maclaurin series, it's centered at 0, plus 0 x squared over 2 factorial, plus 1 x cubed over 3 factorial, plus 0 x to the fourth over 4 factorial, plus 1 x to the fifth over 5 factorial, and so on. So I basically end up with the exact same thing that I originally had, except I don't have the alternating term. So I have x to the 2n plus 1 over 2n plus 1 factorial. Likewise, for hyperbolic cosine, I end up with exactly what I had for cosine, except I don't have the alternating term. And so that's just a little primer on hyperbolic functions.